This video is about permutations, combinations, and the binomial theorem. For our notes, we'll begin with a definition, which is that the notation n with an exclamation point after it is called n factorial, where n factorial, this notation, stands for or means n times n minus 1 times n minus 2 times n minus 3 and so on, all the way down until you decrease these factors and eventually end up with 2 times 1, and it stops there for any natural number n. Now note that 0 factorial is defined as just the number 1, because if you throw a 0 in as the last factor, of course, multiplying by 0 turns everything into 0. So there's a special definition for 0 factorial where we just say it's 1. Now, using that, let's discuss another definition, which is this. A permutation is an arrangement of r items out of n possibilities where the order matters. That's going to come in as very key for us in these definitions as we put them together. The definition, the mathematical definition of a permutation, where again you're picking r items out of n possibilities, is the following. It's n factorial, there's that factorial definition, divided by the quantity n minus r factorial. Now, the notation for this has a couple options that are commonly used. Sometimes you may see the letter P with a subscript before and after it, where the subscript in front of the P is the n. Remember, that's the total possibilities that we discussed. And then the subscript after the P is just the r. That's the number of items you're actually picking out of those possibilities. And that can be used to give this definition that we just defined above. Or sometimes an author will use a capital P and then in parentheses n comma r. Really, either one of these are fine. Notice they both represent this definition for permutation that we defined above, the n factorial over n minus r factorial. Let's try an example where we ask this: how many ways can 4 runners in a race finish in first and second place? Now, in this example, we're picking a certain subset of the total here, right? Because we have 4 runners, that's the total possibilities, but if we're concerned with only those that finish in first and second place, then really we're only picking 2 out of the 4 runners for first and second place. In the case of a race, we would say the order matters, right? There's a big difference between finishing first or finishing second, and so we say the order matters. That's going to help us determine how we're going to set up this process. Now it says how many ways can 4 runners finish in first and second place. So this is the case where we're picking 2 out of 4 possibilities. So we're going to do this a couple ways. First, I'm going to show all the detail by hand. If I have the letters A, B, C, and D representing my runners, those are just, let's say, 4 different people, then we want to know how many ways can those options or those runners finish in first and second place. Let's write out all the combinations by hand first and then see how this might fit with the definition we have above. So first of all, what if we had A finish first and then B finish second? So A and B could be a combination of first and second place, but so could A, C, right? A finishes first, then C finishes second, or so could A and then D. So those really are all the combinations in which A could finish first, and then any of the other runners could finish second. Of course, A can't finish first and second, so we do not have an AA combination. We have these rather. Now, if I do the same thing for B, I could have B finish first, and then I have to have every other combination with it in second place. So what about B and then A? Or what about B and then C? Or what about B and then D? Notice B and B is not there because B can't finish both first and second. Now, observe something carefully here. We had A finishing first and B finishing second in our first set of possibilities. But notice in this second column of possibilities, I have a case where B finishes first and A finishes second. Now, this is where we have to be very clear. If order matters, then those are two different possibilities, right? A being first and B being second is quite different than B being first and A being second. And if you want to be sure about that, just ask an Olympic athlete who's ever won a silver or gold medal. It matters if you're in first or second place. The order matters. All right, so those are the combinations where A could be first or B could be first. As you can probably guess by now, we're going to go through all these other cases as well. So what if C finishes first? Well, C could be first and then A, so CA. We could have C and then B. There's no C and then C, but then you could have C and then D. Again, those would all be the cases where C is first and anyone else would be second. But as you might expect, we'll finish this with wondering when D is first. So you could have D and then A, D and then B, and then D, C for when D finishes first and C finishes second. All right, if you consider all these possibilities, which we've now laid out, you can count them up and you'll find that there are in total 12 possible ways to do this if you just count up every pair we've written out. Now, we've already discussed that this is a case in a race where the order matters, which means we can use our permutation definition above. This would be where we have, out of the total possibilities of 4, we are trying to order 2 of them. So we could call this 4P2 using the notation above, or you could use the other notation and say P of and then 4 comma 2. Either way, it's the same way to represent this formula where n is the total number of possibilities, that's 4. So either way, we're going to say this is really 4 factorial, that's the numerator of this permutation definition. In the denominator, we have n minus r. Well, that would be 4 minus 2. Out of the 4 possibilities, we're selecting 2 of them, and we want that factorial as well. Now, to understand factorial, remember, 4 factorial is really 4 times 3 times 2 times 1. If we just write that out quickly, 4 times 3 times 2 times 1, I think you'll see that the arithmetic's pretty simple here. Down in the denominator, we have 4 minus 2 factorial. Well, really, that's 2 factorial, which is really just 2 times 1. But then the 2's would cancel, and so would the 1's, which means this is really just 4 times 3 over 1, you could say, which is really 12. And notice that's matching the ones we wrote out by hand. Now, the nice thing about having a formula like this is that when the numbers are quite large, as they very well could be, there's no way to write it out by hand effectively, and it even becomes cumbersome for a computer to do at some point. This formula is a really nice, clean summary of it that will give us the actual ways or number of ways that we can have this kind of selection occurring. Let's move on to another definition where we can say this: a combination is an arrangement of r items out of n possibilities. Okay, so this is sounding familiar here, but now where order does not matter. In the permutation definition above, the order did matter. In the combination definition, the order does not matter. Notice the definition mathematically for this one is n factorial in the numerator over, now notice the similarity, there's this n minus r quantity that's factorial, but then there's this extra r factorial written in front of it. So there's an extra factor in the denominator called r factorial. Now the notation of this is very similar, except instead of P for permutation, we use the letter C for combination. So you might see NCR, where N and R are those subscripts. And this is defined the same way we just wrote out. We have N factorial in the numerator, and then R factorial times quantity N minus R factorial in the denominator. And that's true no matter which of those notations we pick for this combination. Now let's try an example of how this might work as well. This one says, how many ways can 2 winners be drawn from a hat containing 4 names? Well, if you can imagine this kind of scenario where you're just drawing something from a hat, you either win or you don't. There is not any specification about first or second place here. You're just getting drawn or you're not getting drawn. So because of that, because of the drawn from the hat, we could say order does not matter for that, which means we're going to use the combination instead of the permutation. So really there's a little bit of interpretation from some problems like this where you have to decide one thing. Does the order matter or not? And you can use the example of the race for the permutation as a good model where order might matter. So a race is a good example of that. Sometimes an election where you're electing a president and a vice president would be the same kind of thing. But then in a combination scenario where the order doesn't matter, maybe it's just selecting things from a hat or something similar where it doesn't really matter which one gets selected first or second or third. It's just whether it gets selected or not. Okay, so in this case, how many ways can two winners be drawn from a hat containing 4 names? Again, now let's write this out by hand first. So let's also start with A, B, C, and D, where let's say those are the 4 names that are in the hat to start. Now we're selecting 2 of them. We want to know how many ways can we do this. Well, let's start writing them out. If I select A and then B, that's one possibility. What if I selected A and C or A and D? Those are 3 different possibilities already. Now if we move on to try the second similar column to what we did in the permutations where we select A, this time we'll start selecting B. And then if I do B and then A, we'll notice immediately an issue where B and A is selected, but remember, if the order doesn't matter, then selecting A and then B is the same thing as selecting B and then A, which means we do not actually want to count both of those because they're actually the same thing if the order doesn't matter. So we're actually going to scratch out one of those possibilities, B and then A. All right, now we're going to go ahead and continue the same kind of pattern though. So B, A, B, C, and then let's say B, D. In the next column, I'll have C, A, but again, notice we had A, C already, so we can scratch C, A out because that's the same thing as A, C. The order doesn't matter, so those are actually both representing the same kind of draw. Okay, we could have C, A, we could have C, B, or we could have C, D. Sometimes it's easiest just to write them out first and then cancel them out. So notice C, B shouldn't exist because BC was already there, and that's the same thing if order doesn't matter. Okay, we'll continue this on, and then we lastly have DA, DB, and DC. But again, if AD was already selected, then we don't need DA. If BD was already selected, we don't need DB. And if CD was already selected, we don't need DC. So you can see how really we start canceling out some of the possibilities because they've already existed just in a different order. And that's why you'll end up with the formula we have above. Notice in the denominator of these formulas, we're dividing by this extra factor, r factorial, as we discussed above. Well, that extra factor, when you divide by it, right, you're dividing the fraction by something bigger, which will make that fraction ultimately smaller, which is why the number of possibilities you have decreases because you're not counting all of these repeats. All right, so let's count what we have now. We're expecting out of all the non-repeats, 1, 2, 3, 4, 5, 6 total. If we now try the formula, we'll say 4C2, and then I'm using, again, 4 is the n value, that's the total, so this is 4 factorial over, and then the denominator now is going to have r factorial. Well, r is the number that we're drawing, so that'd be a 2 factorial times, and then in the parentheses it's n minus r factorial. Well, that'd be 4 minus 2, which is really 2 factorial. If we simplify this result using the definition of factorial, we're going to end up with, in the numerator, just a 4 times 3 over, and then in the denominator just a 2 times a 1. Okay, that's just kind of expanding all these factorials out. You could write that out by hand. I didn't write that step there, but that's what it is, which means we really have in the numerator 12 over in the denominator 2, which of course is 6, and that's what we were expecting from what we found by hand as well. Thirdly, let's talk about another definition called the binomial coefficient. Now, take a look at the way that this is written. There's some new notation here, and that is we're looking at some parentheses, but these parentheses contain 2 numbers that are just kind of hovering one above the other, but it's not a fraction, okay? So we see n over the letter r, but there's no fraction bar between them. It's just n above r, you could say. All right, but that is defined, this binomial coefficient, for which that's the notation, is defined as n factorial in the numerator over r factorial times n minus r factorial. Now, wait a minute, that actually should look very familiar. If you look above at what we just discussed, that's the exact same as NCR. That is the definition for a combination that we have defined above. So this fraction of this ratio matches our definition of a combination above. And so now what we're saying is that that is called the binomial coefficient, and then there's just this new notation where you put those two numbers, n above the r, but not in a fraction, in parentheses. Now, just for the sake of some shortcut notation, or at least verbiage, for this binomial coefficient, when you see it written where you have n above the r, then sometimes you'll hear people say n choose r. Okay, so you'll hear this sometimes, n choose r. And that's sometimes it's a short way of saying this binomial coefficient, where n, again, is that top number and r is the bottom number. Now, I'm going to use that kind of verbiage just to help simplify the language of this next theorem. Next, we have what's called the binomial theorem. And this is a theorem that will allow us to expand something of the form a plus b in parentheses to the power of n. So that's a familiar algebraic structure that we've been working with for quite a while, but we've mainly seen it in some simple forms where n is usually no bigger than 3 if we're actually expanding by hand, most commonly 2 if we're squaring some binomial. But the nice thing about this binomial theorem is that it's a shortcut way to expand it for any natural number n, which can get quite large. Now, there are two ways to write this formula out, and so I'm going to read both of them. The first one is when we say this. The quantity a plus b in parentheses to the power of n could be written as the binomial coefficient in the following way. It's n choose 0 for the first term, then it's n choose 1 for the second term, then n choose 2 for the third term. Okay, are you seeing the pattern here? The next coefficient would be n choose 3, n choose 4, all the way up, continuing on until the last term has the coefficient n choose n. So how many terms you have depends on what n is. All right, now those are just the coefficients, the binomial coefficients. Now let's go ahead and look at what's after those for each term. In the first term, we have n choose 0, but then after it is a to the power of n. Well, remember, a is coming from that first term in the binomial we started with. Okay, in the second term, we have a to the power of n minus 1. Okay, notice a descending order of powers here. The first one was a to the n, then a to the n minus 1. But then we have this b popping up right with it. So it's the second term has a to the n minus 1 times b. You may say, well, wait a minute, where was b in the first term? Well, it wasn't there, but that's actually because you could have put a b to the 0 power next to that a to the n. Of course, b to the 0 power is 1, and you wouldn't normally even see it show up. But in case it helps recognize the pattern here, I just want you to know that there really is a b to the 0 there. And then you could think of this second term as having really a b to the 1 instead of just a b, right? But this will help you recognize the pattern. Notice what's happening here. We have a starting out with the power of n, and then decreasing with every term. So the first term has a to the n, the second has a to the n minus 1, the third has a to the n minus 2, and so on. Okay, hold on. Notice what's happening with the b factors. So we had b to the 0, then b to the 1, then notice it's b to the 2. Okay, can you find the pattern that's happening here? The powers of a are decreasing by 1 from n. The powers of b are increasing by 1 from 0. And they're just kind of alternating this pattern where a is decreased, the power of a is decreasing, the power of b is increasing. This will continue all the way down the line until, notice what's happening at the end. So we have this a, nope, that's actually a typo there. This last term should not have an a factor, so I'm just going to scratch out that a for a second. It should only have the b to the n. Sorry about that. Okay, so that's really the last term. So notice what's happening. Remember, the a that's not actually supposed to be there, that you could imagine as an a to the 0 power, which is actually 1, kind of like we saw with the b to the 0 power up in front. And so that a to the 0 power wouldn't show up. It would just be a 1, which means this follows the same pattern. So notice the a's start with the power of n, and they go all the way down and decrease until a has the power of 0. Okay, but in the other direction, b starts with the power of 0 and increases all the way until the last term where b has the power of n. So there's this alternating pattern going on here. Now that will help us understand how to apply this theorem to an example. Now there's another way to write out this theorem, and that's in series notation with the sigma symbol. So you could also say this: the quantity a plus b to the power of n is the sum from I equals 0 to n of the binomial coefficient of n choose I times a to the n minus I power times b to the I. Either one of those works fine. Sometimes the sigma notation looks a little more intimidating and harder to understand at first, so writing it out can help like we did here. Furthermore, we could say this: the binomial coefficient, which we've been using here in this definition, can be computed easily using Pascal's triangle. It's kind of a shortcut way to do this by hand. Of course, if you're using a calculator, this all can be done quickly that way, but sometimes by hand the triangle is even faster. So let's try an example now where we want to use the binomial theorem to expand x minus 3y in parentheses to the 5th power. Now I want to show you an example of this using Pascal's triangle. So let's first of all recall what that is. Maybe you've seen this recently, maybe not recently, or maybe not at all. Pascal's triangle is just a numeric triangle that kind of looks like a tree, where you start with a 1 at the top, and then in the second row you put 2 1s kind of beneath that first one but surrounding it. Okay, but then every row after that is made up where a number, like let me pick on the third row where n is 2. That third row reads 1, 2, 1. Okay, well, where did the 2 come from? Because every number in Pascal's triangle, except the outer numbers, which are all 1s, okay, every number comes from the numbers that would be directly feeding into it. So the 2 in that third row comes from the 2 1s that are kind of above it diagonally that would add together to give you the 2. Now that's true of all other rows as well. If we go on to where n is 3, which is actually the 4th row because we're starting where n is 0, okay? But in where n is 3, you'll find 3s in the middle of this row. Well, those 3s come from diagonally above each 3 is a 1 and a 2, which would be added to give you the 3. Same thing for that second 3 as well. This is true all the way down, so in the next row you'll find a 4, well that comes from the 1 and the 3. You'll find a 6 in the middle that comes from the 3 and the 3, and so on. Okay, so this is the pattern of Pascal's triangle. The nice thing about Pascal's triangle is that it actually summarizes the binomial coefficients for us. So in this particular example we're working with, let's go ahead and kind of lay things out. Notice the power of this x minus 3y was 5. That tells us that n equals 5. So we're actually working in that row where n is 5. But let's go ahead and pick out a couple other things. So if you compare this to the definition above, we would say a is this first term, which is x. And we would say b is, now notice in the formula above it was a plus b to the n. This particular example has a minus sign. Well, that's fine. That could be considered like x plus negative 3y. And that means that b is actually negative 3y. And we're going to use that when we start to put this all together. Okay, now, the best way I think to write this out is to start with the coefficients and then try to write out the rest from there. So let's go ahead and write out the original problem. That was x minus 3y all to the 5th equals, and then we're going to write out, first of all, just the coefficients. We're talking about where n was 5, so that's the last row we have written here in the Pascal's triangle. I'm just going to write out those coefficients in the order in which we see them. That was 1, 5, 10, 10, 5, 1. But I'm going to leave some space. So I'll say 1, 5, 10, 10, 5, 1. Hopefully I've left enough space to fit everything in there. But those, again, are just the coefficients coming directly from Pascal's triangle. Now, those are the binomial coefficients, which could have been computed way back up here using the definition of our binomial coefficient. which you can do with a combination, as we've defined that. But we're just using the shorter cut of Pascal's triangle to get those down. Now, what I'll do after those is start, given this definition of the binomial theorem, by putting all the a's in there first. So remember, a was x for this example, so I'm going to put an x after each one of these coefficients. Okay, now we have to go back and fill in the powers of x, which we'll do next. You'll recall from this definition of the theorem, we start out with a to the n. That's the first term. So in this case, n was 5, which means I'll have x to the 5th for the first term, and then they just decrease from there. So x to the 4th is next, x to the 3rd after that, and then squared, and then single, and then remember that last term is a to the 0. Okay, I'm going to put that in here as x to the 0. Obviously that would be 1 and it would disappear, but just for the sake of clarity, I'm going to put that in. Okay, that's all the a terms, which we've identified as the x. Now let's go ahead and put all the b terms in. Remember, b is negative 3y. So I'm going to put negative 3y in after all these x's. So it's pretty cluttered here to try to squeeze this all in, but we're going to rewrite this in a much simpler form in 1 second. So let's just hold on for now. Now, you'll recall from the definition of this theorem that those b terms, which end up as b factors per term here, those start at b to the 0, and then they increment all the way up to b to the n at the end for the last term. So we'll go ahead and follow that pattern where I put the 0 power for the first of these negative 3y's, and then the 1 power, and then 2, incrementing all the way up until the last term, which would have a 5th power for that b value of negative 3y. Okay, so it's clearly very cluttered. Now, very importantly, between all of these terms, for which there's not much space, would be a plus sign. I'll go ahead and put these in a different color. That might help a little bit. So separating each one of these terms that we're now piecing together should be a plus sign. And that will help us to distinguish how many terms we have and what they are. Our next job is simply to rewrite everything in just a cleaner fashion. Now notice the first term was 1x to the 5th times negative 3y to the 0. Well, the 1 wouldn't show up, and nor would the negative 3 to the 0, nor would the negative 3y to the 0, because that's also 1. So really, it's just x to the 5th for the first term. Continuing on to the second, we'd have the coefficient of 5. Then we have x to the 4th. And then we have this negative 3y to the 1st. But, okay, so this is where it gets interesting. If this is a negative 3 as part of that factor, really we'd multiply that negative 3 with the 5, which means we'd end up with a negative 15 coefficient for that second term, and then it'd be a y to the 1st, which is just y, so we can copy that in. All right, so this is how it goes. We're just kind of cleaning things up. Thinking ahead a little bit on the next term, notice what's happening here. We have a 10 already written for the coefficient, but then after, for the b value of negative 3y, that was squared in this term, notice you'll have a negative 3, but it's squared, so that's really going to turn into a 9, which you'd multiply by the 10. A positive 9 times the 10 really means we have plus 90 as the coefficient for that term, and then the variables would end up as x to the 3rd and then y squared. We continue this idea going all the way down. Thinking of our next term, okay, it already has a coefficient of 10, but let's not forget that after it we had this negative 3 to the 3rd. Okay, well, if you expand that, that's really negative 27. We'd multiply that by the 10 to end up with a negative 270 as that coefficient ultimately. And then we'd have an x squared with it, and then really a y cubed. In the same way, if I were to keep going, my next term would be a plus 405 x y to the 4th, and then minus 243 y to the 5th. And that takes us all the way to our last term, simplified. And so this this remaining expression would be the expansion of x minus 3y all to the 5th power. So you can imagine going the long way on this would be writing out x minus 3y as a binomial 5 times multiplied with itself. It'd be a nightmare of combining like terms and foiling and distributing. This is a severe shortcut to that whole process, and the binomial theorem will do it given everything we've just defined with it.